In this video, we're going to balance the redox equation for the combustion of methane in a fuel cell. Fuel cells are an interesting alternative to combustion of fossil fuels because they are much more efficient. Much less energy is lost as just heat wasted out into the surroundings. And so, therefore, you need to consume less fuel than you would if you were simply burning your fuel. So the reactions in fuel cells are still combustion reactions. So in this case, we would be reacting methane gas with oxygen gas to produce carbon dioxide and water. And because fuel cells run at ambient temperature, the water would be liquid rather than a gas. Now, sure, you could just balance this by inspection and you would have all of the elements balanced. But if you do that, you're not going to be able to do any electrochemical calculations because you're not going to know how many electrons were transferred from your oxidized species to your reduced species. And so we're going to break this out into half reactions so we can extract that information. To do that, we're of course going to have to start off by assigning oxidation states to all of our species. So the oxygen atoms in oxygen molecule have an oxidation state of 0. We've already assigned oxidation states to the atoms in carbon dioxide and in water earlier in this course. And we saw in one of our other examples that hydrogen is very slightly less electronegative than carbon. As such, in methane, the hydrogen atoms have an oxidation state of +1. Leaving the carbon atom with an oxidation state of -4. So looking at this, we can see that the carbon atom in methane has lost a significant amount of electron density, having its oxidation state go from -4 all the way up to +4. So those will be the species involved in our oxidation half reaction. Starting with methane and ending up with carbon dioxide. Our reduction half reaction is going to involve the reduction of oxygen with an oxidation state of 0 to a product in which it has an oxidation state of -2. And the appropriate product to pick is going to be the water, because if you pick the carbon dioxide, you're never going to get that half reaction to balance, because how are you going to deal with the carbon? So our reduction half reaction is going to involve oxygen gas going to water. Fuel cells typically operate under basic conditions, so we will balance initially under acidic conditions, but then convert to basic conditions. Because we have hydroxide and water available to us, we don't have significant amounts of solvated protons available to us. So to balance the oxidation half reaction, I balance everything except oxygen and hydrogen. That's the carbon. That's done. Then I add water to balance my oxygen atoms. So I'm going to add 2 water molecules to my reactant side. Now I need to add solvated protons to balance my hydrogen atoms. I have 8 hydrogen atoms on the reactant side. So I need to add 8 protons to the product side. And then to balance out the charges, I'm going to also need to add 8 electrons to the product side. Because this is in base, I can't leave my solvated protons there, so I'm going to have to add 8 hydroxide ions to both sides of the equation. The 8 protons and 8 hydroxides on the product side combine to make 8 water molecules. And the 2 water molecules on the reactant side are going to cancel out with 2 of those 8 water molecules, leaving me with 6 water molecules. For my reduction half reaction, balance everything except oxygen and hydrogen. Pretty straightforward. There's nothing except oxygen and hydrogen. Balance my oxygen atoms by adding water, so I need a second water on the product side of the reaction. balance my hydrogen atoms by adding solvated protons. So I'm going to be adding 4H plus to the reactant side, and I'm therefore going to have to add 4 electrons to neutralize the charge. Again, I'm actually operating in base, so I now need to add 4 hydroxides to both sides of the equation. The 4 protons and 4 hydroxides on the reactant side combine to make 4 water molecules, and the 2 water molecules on the product side are going to cancel with 2 of those water molecules on the reactant side, leaving me with 2 water molecules on the reactant side. I'm now going to go ahead and tidy these up a little bit before we start adding them up. So we can see here that our oxidation half reaction produces 8 electrons. Our reduction half reaction is only consuming 4 electrons as written. So in order for it to fully consume all of the electrons released by the oxidation half reaction, we have to double everything and then add those up. So if I go through and I double all of my coefficients on my reduction half reaction, I'm going to have 2 oxygens and 4 waters and 8 electrons to give me 8 hydroxides. And then I add everything up and I get CH4 gas and 8 hydroxides and 2 oxygen and 4 water, giving me carbon dioxide gas and 6 water and 8 hydroxides, because the 8 electrons cancels. But that's very important information. It's really the whole reason we went through this process, is to note that the number of electrons that were transferred in this reaction per unit as written is 8. We can see that our equation could stand some simplification. We have 8 hydroxides on both sides, so they cancel out. We have 4 waters on the reactant side and 6 on the product side, so 4 waters cancel with 4 of those 6 waters, and that gives us an overall balanced equation of CH4 and 2 oxygens reacting to give CO2 and 2 water molecules.